Good friends. Okay, coming to the third problem on Rayleigh ridge method. Okay, so here already we studied about two numerical problems on Rayleigh ridge method. Okay, so it is also called as shortly RR method. Okay, so I told many times, so if you want to solve Rayleigh ridge method problem, you have to remember the six formulas of different beams. Okay, so if you knows those formulas, then we can solve easily by what, with help of this Rayleigh ridge method problems. Okay, so here the main purpose of using this Rayleigh ridge method is nothing but what, it is an analytical method to find the deflection at a different point in a given beam. Okay, that is the main purpose you are going to use this Rayleigh ridge method. Okay, in today's class I am going to tell you about the third different types of problems. Okay, that is a bar having a load is acting what uniform, that is what UDL, that is uniform distributed load acting on that particular bar. Okay, so look at the question is given like this. Okay, I will read out here. Problem number third, that is using a Rayleigh ridge method, determine the maximum deflection of the beam fixed at the both the ends subjected to UDL, that is P naught, over the entire length as shown in the below figure. Take, let us assume our E is equal to Young modulus, I is equal to moment of inertia, and A is equal to area of cross section. Okay, so this is a beam is given, both the ends are fixed at the length of L, and both, that is at point A, at point B, both ends are fixed, that is where the deflection going to be 0, and P naught, that is a load is acting uniformly distributed load over the entire length of the given bar. Okay, you need to calculate what, determine the maximum deflection of a beam. Okay, where is the maximum deflection in the given beam, you have to calculate by using what, Rayleigh ridge method. Okay, that is RR method. So how to find, I already told you, if you want to solve this Rayleigh ridge method problem, you have to remember, or you have to analyze the list of formulas first. Okay, that already I given in the first class, that is in the introduction class on this Rayleigh ridge method. Okay, so that is here, this is the problem. So it is UDL means what is the formula for this. Okay, that is strain energy and work potential formula is what. Okay, for the beam with having UDL load. Okay, go on, apply the procedure. Okay, step number one is what, formulate the potential energy function, that is potential energy function is given by pi is equal to strain energy plus work potential. Okay, so this is a formula for to calculate the potential energy equations. Okay, so we know that the strain energy is nothing but what, the stored energy in the given beam, and work potential is nothing but what, it is due to the external force. Okay, so the where strain energy is the stored energy in the given beam, so which is given by what, strain energy is equal to EI by 2 integration of 0 to L dou square V by dx, and work potential is equal to what, it is due to the uniform distributed load, that is external load, which is given by what, work potential is equal to minus integration of 0 to L P naught into deflection, V stands for deflection here. Okay, into dx. Okay, so once if you know these two equations, these two final equations, you have to substitute these two equations in potential energy function equation. Okay, that is pi is equal to, after substituting this equation, we are going to get this equation. Okay, that is pi is equal to what, EI, where E stands for Young modulus, I nothing but the moment of inertia. Okay, EI by 2 integration of 0 to L dou square V by dou x square whole square dx minus integration of 0 to L P naught into deflection into dx. Okay, so give equation number 1. Okay, so but we know that this is which order, this is a second order. Okay, so assume polynomial displacement function then. Okay, so we know that for a beam fixed both the ends, displacement function is given by, this is the displacement function for given beam. Okay, that is displacement is equal to A4 x to the power of 4 plus L square x square minus 2L x cube. Okay, this is a formula for polynomial displacement function for beam fixed at both the ends. Okay, you have to remember this formula also, this and this. Okay, so now substitute the displacement function into potential energy function. Okay, so now you substitute here, you have to go on do the integration here, dou v by dou x we want. Okay, up to square. Okay, so dou v by dou x A4. Okay, so differentiation with respect to x, you are going to get 4x cube minus 6L x square plus 2L square x. Okay, again differentiate this with respect to x, A4 here, so 4 into 3 is 12x square minus again 6 into 2 12 x. Okay, again here 2 L square. Okay, this is a constant, x is constant. Okay, so we got the value of dou square V by dou x square. Okay, now you this value. Okay, this value you have to substitute in the potential energy function equation, in this equation, that is from equation number 1. So after substituting 1, you are going to get pi is equal to EI by 2 integration of 0 to L 8 4 to the square this bracket 12x square plus 2L square minus 12L x whole square dx. Okay, this is a square minus b square, that is what you have to substitute this equation. Okay, here. Okay, so minus integration of 0 to L P naught A4 x x to the power of 4 plus l square x square minus 2lx into dx. Okay, once if you substitute this, so again you have to re-simplify this. You are going to get this equation pi is equal to 48 after integration of 0 to l, that is 48 ie l to the power of 5 whole divided by 120 a4 square minus pl to the power of 5 divided by 30 into a4. Okay, so once if you doing the integration, so you are going to get the minimum potential energy function pi is equal to like this. Okay, so here how many unknowns are there? A4 is the unknown is there. So differentiate this potential energy function is to be minimum. Condition is dou pi by dou a4. Okay, the dou a4. Okay, so if you that is what dou pi by dou 4, which is equal to 0. So I is the number of order unknown. Okay, there. Okay, so dou pi by dou a4 is equal to 48 ie length to the power of 5 by 60 a4 minus pl to the power of 5 divided by 30 which is equal to 0. So this is goes to this direction, which is equal to 0. So here a4 is equal to what? You simplify, you are going to get pl to the power p naught, that is the load, p naught l to the power of 5 by 30 into 60. This goes to the top direction, that is 60. 48 ie l to the power of 5. Okay, so which is equal to, so 30 to this cancel, going to get 2. Okay, that again 2 divided by this 24 you are going to get here, p naught divided by 24 ei. Okay, so this is what the a4 value you got. Okay, but we know that displacement at any point for the given fixed beam is equal to what? Displacement u is equal to p naught by 24 ei. Okay, so x to the power of 4 plus l square x square minus 2l x cube. Okay, so we know that a4 value. Okay, so we know that at the middle position nothing but what? So a4 value you have to substitute. So v maximum deflection at half is equal to, substitute x is equal to half. Okay, at middle means half, that is x is equal to half, total length is equal to l. So after substituting l here, that is x is equal to half, then you are going to get p naught l to the power of 4 whole divided by 384 ei. Okay, ei, like this you have to calculate the total, that is the deflection at middle point of the given beam. Okay, like this you have to calculate the problems on Rayleigh-Ritz method for different beam. Okay, so like this you have to calculate what the beams which is what the deflection in the given beam. Okay, so in the both the problem okay, that is a Rayleigh-Ritz method and Gallagher method. If you look, questions is same for both the method. Okay, but the way of procedure is different. Okay, so after looking the question, you have to analyze, you have to remember the formula, that is you have to observe the diagram. So which, whether it is belongs to the beam, that is bar is, that is beam is subjected, simply supported beam is subjected to a beam or UD, that is what UDL or uniform varying load or point load, cantilever beam, like that you have to analyze. Okay, based on the given diagram, given requirement, you have to note down the formulas in the, that is strain energy and work potential. Okay, so those strain energy and work potential you have to substitute in the equation, that is in the potential energy function equation. Then you have to re-simplify this, then you have to apply the boundary condition, that is with help of polynomial function. Okay, then you replace the potential energy function, then calculate the how many unknowns are there, that is number of unknowns are there in the potential energy function, then apply the condition, minimum potential energy condition, then you are going to get the maximum deflection strain in the given beam. Okay, like that you have to solve. Again I will repeat this. So look at this here. So again I will repeat the same problem here. Okay, how to solve? So pi is equal to strain energy plus work potential is there. This is the, you know, this is, you know, substitute this equation is there for strain energy, work potential for this, substitute in this equation. First equation you are going to get the first equation. Okay, so here dou square v by dou x square will be there. Okay, we know we should calculate this value. To how to calculate this value, we know the polynomial function for beam both the end fixed, which is equal to like this. Okay, from this equation you have to calculate dou square v by dou x square. Okay, so we calculate dou v by dou x, dou square v by dou x square. Okay, substitute this equation in the, that is potential energy function. Again you have to integrate this. We are going to get pi is equal to like this equation. Okay, then here how many a4 is unknown is there, so minimum potential energy is to be unknown. I have to differentiate, that is dou pi by dou a4, which is equal to like this. From this equation this goes this direction. Okay, that is which will become 0. So from this equation a4 you are going to get, okay, a4 is equal to like this value, but displacement at any point we have the formula, that is v is equal to what? V is equal to this equation. Okay, this is the displacement at any point. Okay, so in this equation you have to substitute the a4 value. So after substituting a4 value you are going to get v is equal to, v stands here displacement. Okay, so v is equal to p naught by 24 ei x to the power of 4 plus l square x square minus 2l x cube. Okay, so then deflection at midpoint is equal to what? Total length is l and middle point x is equal to half. So put substitute x is equal to half in this equation. You are going to get maximum deflection at the middle point is equal to p naught l to the power of 4 whole divided by 384 ei. Okay, this formula for deflection at the middle point subject to a uniform distributed load and the beam is subject to both the ends are fixed. Okay, like this you have to calculate the problems on Rayleigh ridge method with respect to the beams. Okay, so I hope you understand, I think. Okay, so the final answer is there. This final answer in the next upcoming problems, this final answer we are going to use directly one direct. Okay, so what is the deflection of the beam? Can deflection of the beam for the UDL, both the ends are subject to fixed, means we have to use this formula, that is P naught L to the power of 4 whole divided by 384 AI. Okay, so this is the way to solve the numerical problems on Rayleigh ridge method. Okay, so Rayleigh ridge method, what it is, a analytical method to find approximate solution. Okay, so to determine the stresses, strain, deflection present in that. Okay, so and here I used these images from the SB Halle's textbook, that is referred by SB Halle's textbook. You can refer that also. Okay, if you have any doubt, means you can call me or WhatsApp me. Okay, so here like this you have to solve the problems for Rayleigh ridge method. So next class we will move on to the Galley-Curran method problem. Okay, so that is also most important point for the examination. They may ask you one question from Galley-Curran method also. Okay, so it is similar to that type of only, this the Rayleigh ridge method type only you can solve in the next class. Okay, so Galley-Curran is also it is a similar to a type of this Rayleigh ridge method only. So it is also a approximation solution we have to find out. Here there also we have some set of formulas. Okay, Galley-Curran formula is there. Finally that is also called as weighted residual method. Okay, so we will solve the Galley-Curran method problem in the next class, and I hope you understand the Rayleigh ridge method problems. Okay, so here I will repeat again. If you want to solve Rayleigh ridge method problem, you have to remember the 6 formulas of the different beams and bars, that is a work potential and strain energy. Then go for procedure, you are going to get the answer. Okay, so without remembering the formulas, if you go on solving a Rayleigh ridge method problem, means it is cannot. Okay, you cannot solve. Okay, so I hope you understand the Rayleigh ridge method. Next class we will move on to the Galley-Curran method problems, numerical problems on Galley-Curran method. Okay, thank you.